This one was a little bit more of a challenge, right? Stretched our intellectual muscles a little bit more. This one actually comprised of like almost everything we've been doing right since the beginning of the semester, if you really look at it. Had lots of components to it. So the problem here, 105 states we have a 10-foot boom, and it's acted by this 840-pound force in a negative check, right? We got 840 pounds. It says determine the tension in each cable and the reaction at a ball and socket joint at A. Remember what a ball and socket joint is, right? The free body diagram? It freely rotates around, right? But it has support reactions for the X, Y, and Z, but it has no moment, right? It doesn't support any moment. So from a free body diagram standpoint, I would replace this ball and socket joint with, I'm gonna put them all in positive, right? Because I'm a positive type of guy. AX positive, AY positive, and AZ positive, okay? So we're doing a free body diagram of boom ABC here. And then I got the tensile force in the two cables. The cables I'm gonna remove, and the tensile force is acting equal and opposite to each other, so the free body diagram would show TBD and TBE. They're vector forces. It'll look just like that, right? Does that FBD make sense to you guys? So far, so good? Good. Yeah, it doesn't support any moment at the ball and socket. So, let's look at this, right? So I remember we did a problem similar to this, right? Chapter 3. But in that problem, it just wanted to know what the tensile force was, I think, in a cable like over here, right? And it gave us the tensile, that gave us the force in the other cable. This time it didn't give us any forces, did it? So, I guess my question to you guys is, how would you go about solving this thing? We know step 1 is the free body diagram, right? What would be the next step?
So, do some moments at A, get rid of the 3 forces there, and try to find the tension.
Yeah, but just get maybe a step or two along the way, right? Like, what would be the first thing I would want to do? What?
Unit vector?
Yes, exactly. Apply the unit vector concept, because we need to take these forces and reduce them to their rectangular components, right? Then I could sum a moment somewhere, and A is definitely the spot we want to deal with that, right? To eliminate this, so we can reduce it just to TA and TB, and their moments with respect to that. In fact, let's take a look at TA and TB for a minute, or TBD and TBE. They're both located at the same spot on the beat, right? So they both have negative 6i, and they both have positive 7j. And they're equal and opposite to each other, aren't they? With 6. So they have the same geometry, just opposite sense, right? In the Z. So what does that tell you about the Z component force of the BD and BE?
They'd be opposites and coupled.
They're opposites and
Equal.
equal. Very good. So the Z component, right, is opposite. If the Z component of TBD and the Z component of TBE is equal, what does that say about AZ?
It negates 0.
It's 0. Very good. AZ is equal to 0. We already have an answer, right? It asked us for the reaction. That's one of them, right? We still have to get AY and AX, but we know AZ is 0. Because they're negative, right? They're equal and opposite to negative. Now these have both negative 6s and positive 7s, so that's a little different. So let's now use the unit vector concept to reduce, right, these forces in the cable in terms of its scalar magnitude of TBD and TBE, right, and develop its unit vector, and apply the unit vector with the sum of the moments, right, at A with R cross F, with 3 separate determinants, R cross F, R cross F, and R cross F, right? And then we can resolve that from there. So let's start, right? So I'm going to say, well, we've got vector BD. BD is negative 6i, positive 7j, negative 6, it's in feet, right? Feet I, plus 7 feet j hat, and plus 6 feet scalar magnitude, the square root of the sum of the squares is 36, 36, and 49. 121, square root of 121 is 11, right? 11 feet. And then we're going to do the same for BE, right? So we take vector BE, and again, negative 6i, positive 7j, this time it's negative 6k, right? So it's negative 6 feet I hat plus 7 feet j hat minus 6 feet k hat. And since all of the components are the same, we also know its scalar magnitude is also 11 feet, right? The physical distance along here from B to D or B to E. So I'll just write that out. BE is equal to 11 feet. So, in order to express BD and BE in terms of their rectangular components, right, we want to apply the scalar magnitude of the force at BD and BE with the product of its unit vector, right? So writing this out, I would say the vector force TBD is equal to the scalar magnitude of TBD and the unit vector lambda, right? Along that line, BD. They didn't give us this, right? So we leave that in terms of TBD, and we write out the unit vector. Negative 6i plus 7j plus 6k hat, all over 11. So its unit vector, rectangular components, is just negative 6/11ths I plus 7/11ths j plus 6/11ths k hat. And it's, right, and the product of its scalar, TBD. And then I do the same for TBE. TBE is equal to the scalar of TBE and its product of its unit vector. TBE, and this time it's negative 6i plus 7j minus 6k, all over 11. Negative 6/11ths I plus 7/11ths j minus 6/11ths k TBE. Okay, so we can place these, right, components, rectangular components, in our determinant, right? We need to know what the position vector is for each one of those forces. RB with respect to A, I'll write that right here, RB with respect to A is equal to what? What do you guys think? What's the position vector for B with respect to A?
Just 6.
That's it, it's positive 6 feet I, right? 6 feet I, and how about C with respect to A? Positive 10, thank you. Positive 10 feet I. Okay, so, now that we know that, like you said earlier, we're gonna sum a moment, right? With respect to point A. Sum of the moments at A is equal to 0, right? 0 is gonna be equal to R, B with respect to A, cross TBD, right? Plus RB with respect to A, cross TBE, plus that 840-pound force, right? And its position vector, RC with respect to A, cross negative 840 pounds. So we're gonna have 3 determinants, and I can express it as such. I, J, K. RB with respect to A, we just said it was 6 feet, right? 6, 0, 0, and it's the components of TBD is negative 6, positive 7, and positive 6. Negative 6/11ths, 7/11ths, and 6/11ths, right? And I'll just put the constant outside here, TBD. Plus RB with respect to A again. 6, 0, 0, and again, negative 6/11, 7/11, and don't forget that this is now in negative, right? 6/11, and that's TBE. And what the heck, I'll put this in the final determinant, right? RC with respect to A is equal to 10 feet up, right? So it's 10, 0, 0, and this is negative 840 in a jet, right? So this is 0, negative 840, and 0. So far, so good? I resolve the determinants. When I resolve these determinants, I'm gonna get a bunch of components, right? And because these are moments, right? And all of these forces are intersecting with the x-axis. So we have no I moments, do we? All the x components will yield a 0 I. So when you resolve these three determinants, you should automatically say to yourself, I better not have an I in there, right? It should be J's and K's. And once we know these in terms of J's and K's, we can then take them and combine them together, right? The sum of the forces of x, the sum of the forces of y, and the sum of the forces of z is equal to 0 when it's in equilibrium. Based on that, I'll have two equations with two unknowns, so I could solve the TBD and TBE. So resolving this determinant, right, you're gonna get a solution that looks like this. 42/11 TBD K hat minus 36/11 TBD J hat, and then we got TBE, right? And it's the same thing. 42/11 TBD, and this is a positive instead of a negative when we resolve it. So this should be 36/11 TBE, and then we've got the 840 pounds up there, right? 840, or negative, I should say, negative 8,400 K high, where these units are all in terms of foot pounds, right? I like this out, right? This should be K hat and J hat, right? Yeah, J hat, and this is K hat. So now I combine my K's and J's together. Combining the J's together, I'm gonna get negative 36/11 TBD, right? So it takes care of that. And then 36/11 positive TBE is equal to 0, right? So all that tells me in the end is TBD is equal to TBD, which is what we would kind of expect, right? Because these cables have the same geometric configuration. So TBD is equal to TBE. Equation 1, right? Simple. Looking at it from K hat standpoint, we have 42/11 TBD plus 42/11 again, right? TBE minus the 8,400K, and we set all of that equal to 0. Now I can solve for TBD or TBE, they'll be the same, and it's gonna be 1,100 pounds. TBD is equal to TBE, which is equal to 1,100 pounds. And all that just to get the two tensile forces in the cable, right? And we're still not done. Now that we know what the tensile force is here and here, right? 1,100 pounds and 1,100 pounds. How do I get the support reactions here for AX, AY, and AZ? What do you guys think? How would we go about solving for those?
Sum of forces.
Yes, are equal to 0, right? For X, Y, and Z. We already know AZ is equal to 0, so when we do the sum of the forces of Z, they better cancel out, right? So if we sum the forces with respect to x and we set it equal to 0, 0 is equal to ax positive, right, that we show on our three-body diagram. And then we take the x components, negative 6/11 and negative 6/11. TBD plus negative 6/11 TBD. Right? When I solve for that, what am I gonna get? That negative looks like part of the brackets. I'm gonna get AX is equal to 1,200 pounds, and it was a positive answer. So I'm gonna force is a Y. 0 is equal to AY, we set it as positive, plus 7/11 and 7/11, right? TBD plus 7/11 TBE minus 840, right? Don't forget about that. Minus 840 pounds, right? Again, we substitute in for TBD and TBE, the 1,100 pounds, right, into the equation. And we solve for AY. And AY, you should get an answer of, it's negative, I think, right? Yeah, 560 pounds, negative. AY is equal to negative 560 pounds, which means is that it's 560 pounds acting down. At this point, you just sum the forces at Z and set it equal to 0. 0 is equal to AZ plus 6/11 minus 6/11, right? 6/11 TBD plus negative 6/11 TBE. Well, they both, you substitute 1,100, both of them cancel each other out, right? AZ is equal to, which we already knew, is equal to 0. But it's because that is equal to that, right? If this had any other dimension in any other way different from that one, that wouldn't be the case, right? And then I'd have to solve for these with two equations, two unknowns. Right? It took a lot of skills to do that. That's basically what we've been doing since maybe the second week of school, right? Unit vector, right? R cross F, resolve the determinants, and then we use the equilibrium equations finally, right? To find the sum of the forces of X, Y, and Z for the three-dimensional reactions at the supported end. Any questions? Yeah.
So all of chapter 4 questions